Hi, Robin Beaumont here. Welcome to the third tutorial looking at p-values. This time I'm making use of an excellent material by Professor Geoff Cumming, who has just produced an excellent statistics book called Understanding New Statistics, published by Routledge. If you buy only one stats book this year, make it this one. So far, while we have been looking at p-values, we have done so by considering their probability and sampling aspects. We'll now look at how the p-value relates to the fact that it is a statistic and what this means. After we have done that, we're left with only two other aspects to consider: decision rules and consideration of possible alternative measures to the p-value. Let's do a 10-second review of where we're up to. In the first session we looked at the probability aspects of the p-value, that is, a p-value is a conditional probability which considers a range of outcomes. It's often depicted as an area in a graph of its own distribution, if you remember. In the second section we looked at the variability of the estimated mean across samples and discovered that the standard error of the mean, that is the SEM for short, is simply the standard deviation at the cross-sample level. We discovered the remarkable fact that the SEM allows us to predict the accuracy of our estimate, that is, a mean value of our sample across an infinite number of samples of the same size from our one single sample. But now let's move on to some new stuff. What is a statistic? Well, a statistic is just a summary measure. Technically, we have reduced a set of data to one or two values. Here are some examples. The range, that is the difference between the smallest and largest values in the sample. The mean, median and mode. The interquartile range, representing the middle 50% of scores, and the standard deviation and its squared value, the variance, where, if you remember, 1.96 times standard deviation on each side of the mean represents 95% of the scores in a sufficiently large sample when it's normally distributed. We also looked at various transformations of our original values to produce z-scores, t-values, chi-square values and f-values. Finally, we had looked at the p-value, and the p-value is just another statistic. But before we go back looking directly at the p-value, let's take a quick look at the t-value again. So the t-statistic or t-value is basically a ratio of the observed difference between means and that expected due to random sampling. So it's a ratio, but it also takes into account sample size. There are different types of t-statistic or t-value, but for now we will consider the simplest one, the one sample t-value. Let's consider what different values this ratio might take and what this means. When t is equal to 0, the estimated sample mean and the population mean must be equal, because the top value in the ratio is 0. When t is around 1, the observed difference in means is probably around about the same as that expected due to random sampling, because it's going to be around the value of 1. But when we get a value larger than 1, the observed difference in means is greater than that predicted by a random sampling. But the question is, what do I mean by large? And that's what we'll need to look at. You will notice that I've reduced the equation at the bottom to just simply saying signal over noise. Right, let's take a real example. Here we have a random sample of serum amylase levels from 50 healthy subjects, where the mean equals 96 units and the standard deviation is 35 units per 100 mils. We can ask how likely would we have such a mean value from a sample if the population mean is 120. We can simply use our one sample t-statistic formula and attain a t-value. Minus 2.656 looks like a rare occurrence, as we have over 2 times the difference expected from just purely random sampling here in terms of t-values. We can say there appears a big difference between the mean value from the sample compared to the hypothesized population mean. But always remember, we are comparing a sample value, which you know varies across samples, with a population value, which is a constant here. Remember the diagram where I had the arrow going upwards to the population and downwards to the sample. So how does this relate back to probability and specifically p-value? Well, let's look. Well, we can transform our t-value into a probability, just as we did the set of exam scores to produce a probability histogram. Technically, this is a t probability density function having 14 degrees of freedom. There we are. Notice that the top values of this PDF are the original scores and the bottom ones are the t-value equivalents. Also remember that areas under the curve are equivalent to p-values, obtaining a specific range of t-values here, given that the population mean value is equal to 120 in the original units or 0 in t-values, if you look at the top and the bottom of the graph. So just as we did with exam scores and the diastolic blood pressure recordings taken in Glasgow, we can work out the probability of obtaining an observed mean or one more extreme for this specific sample size by calculating the area under the curve to the left of the t-value of minus 2.6 or to the right of plus 2.6. So we can say, given that the sample was obtained from a population with a mean of 120, a sample with a t-statistic value of less than minus 2.6 or greater than 2.6, or one more, in other words, one more extreme than that value, will occur 1.8% of the time, which is just under 2 samples per 100 on average. We can simplify this sentence slightly and say, given that the sample was obtained from a population with a mean of 120, a sample of 15 people producing a mean of 96 or 144 or one more extreme will occur 1.8% of the time. That is just over 2 samples per 100 on average would have a mean value of this or one more extreme. Notice that interpreted unusual to mean here as a difference in either the positive or negative direction. And, as you know, we define this as a p-value. At the bottom of the page I have put the mathematical way that we can say what I've just put into rather complex sentences. Let's take a second look at this mathematical expression. So we can say that the p-value associated with one sample t statistic is defined as 2 times the conditional probability of all those t-values more extreme than the t-value obtained for a specific sample size, given that the mean in the population is a specified value which we call the null hypothesis. Often in textbooks they say the null hypothesis is always 0, but clearly this is not the case. It can be anything as long as it has a single value. For in an example we had 120, which is fine. You can also interpret the above as areas under the t-distribution for a specific sample size. Because the t-distribution is symmetrical, we just need to take one tail area and double it, as we did. We have seen in the above example how the p-value statistic relates to the probability density function for a specific t-distribution made up of t-values. These t-values form what is called a sampling distribution. This relation between the statistic, sampling distribution, probability density function and p-value is basically the essential anatomy of the process of experimental analysis using inferential statistics. As you would expect, many statistics have this type of relationship, that is, statistic, sampling distribution, probability density function and associated p-value statistic. However, not all statistics have mathematically defined sampling distributions and therefore no probability density function and no p-value, in which case it is necessary to use computers to create these sampling distributions by basically creating virtual populations from the sample. Think of it as a form of spontaneous generation. In the sampling session we discussed the variability across samples of the sample mean, and all statistics vary across samples. The p-value is no exception, as we will discover. So, as the p-value is just another statistic, we would expect to have it the characteristics of a statistic. Specifically, by repeating an experiment with another random sample, the p-value would be different. You may also ask, how different will this p-value be? There are problems here with trying to work this out, because it does not follow a normal distribution, which we will see in a minute. Furthermore, the distribution of the p-value depends upon the probability of the null hypothesis being true. Remember, we have so far assumed the null hypothesis is true, but we've warned all this will change in the next session. But for now, we will stick to the belief that the null hypothesis is true. I mentioned at the beginning of this session the excellent stats book by Geoff Cumming, and he has also produced both a set of Excel spreadsheets and a YouTube video to explain the variability of p-values. The YouTube video is called Dance to P-Values, and well worth a look. It goes a little further than I want to in this session, so I'm going to take a little example from it. Here is an extract from Geoff Cummings' YouTube video. This is showing the p-values for subsequent trials of samples size 15 with a mean of 12 and a standard deviation of 3.5. Basically the same as the amylase data, assuming that the null hypothesis is true. I've also created around 1,000 replicants of the experiment, and you can see that while 90% of the p-values from the histogram on the left are more than 0.1, there are some that are very small p-values. There is no way of knowing which one of those values that was going down the screen represents our experiment, as very rarely do we repeat experiments with different samples. This exercise highlights the importance of replication, and please remember this even if you forget everything else in this session. So the take-home message is that we can obtain very small p-values even when the null hypothesis is actually true. That is not just assumed to be true for the p-value calculation, it is when it is actually true. Technically, the distribution of p-values in this situation, that is when the null hypothesis is in fact true, means that there is equal chances of obtaining any value between 0 and 1 for a single experiment, and this is technically called a uniform distribution. So we say that when the null hypothesis is true, the p-value follows uniform distribution. You may be wondering why, because our p-value varies across trials, I have not suggested that we create a confidence interval for it. Well, the problem is that while the p-value is a statistic, it is a summary, that is, it's a summary value for our sample and varies across random samples, as I've mentioned. Not all statistics are estimates of a parameter in the population. It is not the same situation as we had with the sample mean, which you know from statistical theory does represent a single value in the population, even if our estimate from our sample is just a poor shadowy image of it. A single p-value just does not exist in the population. Fortunately, there are ways of getting around this with the idea of expected variability of the p-value across trials, which I will discuss quickly here, but in much more detail in the next session. It is possible to calculate a thing called a reproducibility probability value, which works in a similar way to a confidence interval. It tells us with a particular level of certainty what a certain percentage of the p-values will fall in subsequent replicants of the experiment from a single p-value in a previous experiment, assuming that the null hypothesis is true. But as we'll see in future sessions, it can work when the null hypothesis is not true as well. This approach is very new, and as far as I'm aware, Cummings is the first author to put it down in a book. Before that, it was only documented in research journals, such as Goodwin, who has published several articles, his 1992 and 2001 journal articles being the most cited. Hung, O'Neill, Booner and Cohen published an article in 1997 in the Biometrics Journal demonstrating again its use and described 3 different methods of deriving the value. Also, Shou and Chow in 2002 in the journal Statistics and Medicine specifically considered the situation of how likely it was for one to get a similar p-value in a subsequent trial. Much more recently, in 2011, Booz and Stefani in the Journal of the American Statistical Association recommended that p-values are thought of once again in a more qualitative way, using a single, double and triple star approach, as the actual values are so unpredictable, and discuss again how one can use this idea of a reproducibility probability value. Showing the signs of times also, Booz and Stefani give R code on how to produce the RP value. Finally, we come back to Cummings. His 2008 article is excellent, describing how to understand the RP value, and his book where we can use his actual reproducibility probability value calculator. Details of how to use this calculator, along with what the various options mean, are given in Cummings' book, and anyone can download the software free. Let's take an example. Say we were given from our experiment a p-value of 0.05. What is the interval in which we are likely to see 80% of subsequent p-values? Well, here's the answer. We have 80% of seeing subsequent p-values fall within the 2.22 boundary. That is one-sided. In this instance, I've taken that value. This means we have 20% of them being subsequently more than 0.22. So, we discussed in detail three aspects now of the p-value: how it is related to probability sampling and statistical theory. But we will see in the next session how, by introducing certain rules, we can use the p-value along with other values, be able to make informed decisions. And we'll also be looking in much more depth at the variability of the p-value and how we can use it as a method of giving weight to both the null hypothesis and to possible other hypotheses as well. Bye for now, but remember to get the book by Geoff Cumming if you want to understand these concepts in more depth, or at least read his 2008 paper. Bye. And as far as I'm aware, Cummings is the first author to put it down in a book. Before that, it was only documented in research journals, such as Goodwin, who has published several articles, his 1992 and 2001 journal articles being the most cited. Hung, O'Neill, Booner and Cole published an article in 1997 in the Biometrics Journal, demonstrating again its use, and described 3 different methods of deriving the value. Also, Shou and Chow in 2002 in the journal Statistics and Medicine specifically considered the situation of how likely it was for one to get a similar p-value in a subsequent trial. Much more recently, in 2011, Booz and Stefani in the Journal of the American Statistical Association recommended that p-values are thought of once again in a more qualitative way, using a single, double and triple star approach, as the actual values are so unpredictable, and discuss again how one can use this idea of a reproducibility probability value. Showing the signs of times also, Booz and Stefengi give R code on how to produce the RP value. Finally, we come back to Cummings. His 2008 article is excellent, describing how to understand the RP value, and his book where we can use his actual reproducibility probability value calculator. Details of how to use this calculator, along with what the various options mean, are given in Cummings' book, and anyone can download the software free. Let's take an example. Say we were given from our experiment a p-value of 0.05. What is the interval in which we are likely to see 80% of subsequent p-values? Well, here's the answer. We have 80% of seeing subsequent p-values fall within the 0.22 boundary. That is one-sided. In this instance, I've taken that value. This means we have a 20% of them being subsequently more than 0.22. So, we've discussed in detail three aspects now of the p-value: how it is related to probability sampling and statistical theory. But we will see in the next session how, by introducing certain rules, we can use the p-value along with other values to be able to make informed decisions. And we'll also be looking in much more depth at the variability of the p-value and how we can use it as a method of giving weight to both the null hypothesis and to possible other hypotheses as well. Bye for now, but remember to get the book by Geoff Cumming if you want to understand these concepts in more depth, or at least read his 2008 paper.